So far, the analysis of continuous immobilized enzyme reactors in terms of their performance has been based on the kinetics of the enzyme reaction. We have considered the reactions that follow Michaelis-Menten kinetics, the reactions that follow substrate inhibition or product inhibition. We have also considered approximation with respect to zero order and first order reaction regimes in the case of enzyme catalyzed reactions. Then we had looked at the effect of mass transfer on the reactor performance by virtue of steady state analysis of mass transfer and biochemical reaction taking place simultaneously in a enzyme reactor. And in all this analysis, we have assumed that the flow pattern in the reactor is either well mixed, perfectly mixed, that is the contents of the reactor are homogeneously mixed without any stagnant zones or without any dead pockets in the reactor, or alternatively in the case of a plug flow reactor, the velocity profile of all the fluid streams are flat and it can be described by a ideal plug flow behavior. Now, but essentially the real reactor, although this kind of situation may be practically feasible in a laboratory experiment where you can have a very high height to diameter ratio and maintain and have a very uniform packing in the reactor, so that the plug flow flow characteristics are realized in the laboratory. But on a large scale reactors which are real industrial reactors, the possibility of achieving the ideal flow patterns, that means either a complete perfect back mix or a perfect plug flow reactor, are usually far from reality, and most of the reactors they operate of course closer to one of the regimes, but they also have a mixed, partly mixed behavior. Now, essentially today we would like to look at the how does this deviation in the flow behavior, ideal flow behavior, influences the reactor performance, how to approach the situation in case if the flow behavior is not ideal in terms of perfectly well back mix or a plug flow behavior. Now, very often we must realize that the causes of deviation from the ideality are essentially because of certain stagnant regions in the case of a reactor. For example, if you consider a plug flow reactor which has been separated by certain horizontal trays just to allow a proper mass transfer, there might be certain stagnant region on the corners, or in the case of a back mixed reactor, if the impeller is not properly designed or the mixing pattern is not properly designed, there might be some region in the whole reactor where the mixing is not uniform and the idea of completely back mix is not realized. Alternatively, there might be some channeling effect. If for example, in a packed bed reactor, if the particles are not of uniform size and the packing is not uniform, there might be some channeling, and with the result that a part of the fluid stream which is getting into the reactor passes through unreacted, and therefore the performance get deteriorated. Then there might be short circuiting, of course something like channeling or bypassing also can take place in the case of a stalled vessel, and whereby you get into some kind of non ideal. Now, in all these situations the performance of the reactor is lowered compared to what we look for by analysis in the case of an ideal fluid flow pattern. Now, also an alternative situation in enzyme reactor is that sometimes we tend to develop reactor designs for various reasons because of the reactor because of the requirements of the reaction. That means, for example, in the case of a recycle reactor, as you notice here, although it is a packed bed reactor, but just to increase the linear flow velocity to overcome the external film diffusion, we may like to have a recycle stream so that the linear flow velocity is increased, but ultimately it will end up in a non-ideal non-ideality from the plug flow behavior. Similarly, in the case of a fluidized bed reactor, we also have the same thing, just to improve the mass transfer and heat transfer effects. In the case of a reactor, the particles are fluidized by the substrate, of course to the extent that the particles are not thrown out of the reactor, they are retained in the reactor, but the voidage increases to a level that they remain fluidized in the reactor. And even in this case, the behavior in terms of the flow behavior, the flow behavior will be somewhere in between the plug flow as well as the back mix reactor. And in another case, if you look at the combined CSTR and ultrafiltration reactor, which is often is one of the model system which has been used for substrate which are solid in nature, and where enzyme is required to be used in soluble form. One can carry out the reaction in a stirred reactor in a CSTR with the possibility of the product stream passing through a ultrafiltration chamber, whereby the enzyme is recycled back and the product is withdrawn from the permeate stream. Now, in this case also essentially the reactor, although theoretically one has considered it is closer to a CSTR, but in performance if you look at it becomes it has a deviation from the CSTR, because the concentration profile in the whole reactor does not remain ideally perfect. Similarly, we have systems like hollow fiber reactor, as we discussed earlier, in which case the enzyme is entrapped in one of the side of the tubes, and substrate is passed from the other side, and the two sides are permeable, that means they are separated by a semi permeable membrane, and the reaction can take place and the product stream can go. Although the system is designed to mimic or at least operate closely to a plug flow reactor, but still in the actual performance, its performance may be slightly inferior than a plug flow behavior, and it might have some kind of a back mixing, partly back mixing. Another very important industrial reactor which has been used is a spiral bound multipore biocatalytic module. If you recall that the immobilized enzyme preparation is in the form of a thin long membrane film, which is wrapped around a central core, and this core and of course the enzyme membrane is also separated by a wire mesh or some kind of a solid support, so that its strength, mechanical strength improves, and this spiral bound module is then inserted into a column, whereby the substrate is fed from one of the ends and the reactor can be operated in a packed bed mode. But of course, again here the spiral bound module really operates somewhere closer to closer to plug flow behavior reactor and not exactly as a plug flow reactor. Now, the extent of non-ideality in the case of a flow pattern, I think the first parameter is that we must be able to identify what is the extent of non-ideality in the case of a enzyme reactor. Now, if we can understand or arrive by some means the distribution of the residence time of the various elements of a fluid which is passing through the reactor with respect to time, and that distribution can give us an idea about the extent of flow pattern. That means, if the distribution, let us say if it passes almost like a plug flow behavior or like a CSTR, one can then compare the two patterns and see that whether the flow pattern in the actual reactor is ideal or what is the extent of ideality. Now, this analysis to monitor the deviation from the ideality for an enzyme reactor in flow pattern is mediated by what we call as residence time distribution. Now, essentially it gives you the distribution of the various elements of the fluid passing through a reactor. That means, the age of various elements in a fluid stream from the reactor in terms of age distribution. That means, what is the duration of the time which each element of the fluid has stayed in the reactor, and obviously that is the residence time, and this if in all cases is equal, let us say same as in the case of space time, then obviously it should be a ideal reactor. If it deviates and the exit age distribution or residence time distribution is essentially given by in the form of a exit age versus time distribution, and one can say that the if this is the total exit age distribution for any given fluid element from a reactor, then your 0 to infinity E dt is equal to 1. Now, if you just consider let us say a very small element in this distribution with having the age between t and dt and t plus dt, then the fraction of the exit stream of age between t and t plus dt will be E dt, and this fractions integrated over infinite time will give you the total fluid which is flowing through this reactor, and the exit age distribution is defined in the sense that the total area under the curve is unity. And of course, now if you consider let us say any fraction at time t1, now the fraction of the exit stream which has a age less than t1 will be 0 to t1 E dt. The fraction of the exit stream which has a age younger than t1. Age means essentially the time spent by an element of the fluid in the reactor vessel, and therefore, and on the other hand the fraction of the exit stream which is older than the t1 will be your t1 to infinity E dt, or obviously this will be 1 minus 0 to t1 E dt, because the total 0 to infinity is 1, and therefore, one can essentially get a picture of and now this residence time distribution experimentally for a given reactor system can give you an idea about the nature of non-ideality of a reactor system in terms of flow behavior. Mind it that non-ideality may also be caused by other reasons like mass transfer, partitioning, or variety of other reasons that we have discussed, but this non-ideality we are talking exclusively in terms of the flow behavior. Now, this residence time distribution is usually determined in the experimental reactors by what we know as stimulus response technique. Now, in this technique usually a tracer, and we define a tracer as an inert material which is put into a feed stream along with the feed stream, and this mind the word that you need a inert tracer which can be detected, that can be detected. Of course, detection is important, because if you cannot detect this inert tracer, it does not serve any purpose. Very often a dye can be used, provided the dye does not interfere in the reaction or it does not get absorbed in the carrier material. A inert dye can be used as a detector, as a tracer system, and it can be obviously by measurement of the colorimetry it can be estimated, or alternatively let us say in the case of a reaction system, an enzyme catalyzed reaction, any other reactant or any other sugar or any other material chemical species which will not take part in the reaction can be inserted, or which should be possible to analyze at the exit age. Of course, very often sometime one ends up finding a difficult situation in choosing a good tracer, then in that case radioactive material could be also used as tracers and so that they can be monitored at the exit stream by measurement of simply radioactivity by the counters. And now this the response is a time record. Then after inserting, you can insert any kind of a feed stimulus. It can be a step input, it can be a delta input, or it can be even a random input, does not make a difference. A variety of inputs, types of inputs can be given, and ultimately at the end of it we need to monitor the response of the tracer in the exit stream bit time, and the record of this gives you essentially a picture of the residence time distribution. That is what usually is followed. And if you look at a variety of types of tracer inputs that are inserted into a vessel, let us say consider this is a vessel, we put a tracer input signal or what we call as a stimulus. Now it can be a random input. In any fashion you just allow some quantity of sort of tracer to be inserted randomly, and of course notice an output which will also obviously be random depending on the flow profile. Then it can be a cyclic input in the form of a waveform, and then output also will be some type of a cyclic output. Then we can have a step input, that means initially the tracer concentration is set at 0, and then it is raised, or suddenly after a time t, after some time it is in the feed stream continuously you supply a tracer at a let us say concentration 100%, and then this input again, that means in the reaction vessel will come out in the case of a exponential behavior. Alternatively, you can also give a pulse input, also called a delta input, where over a very short period of time, that means your delta t approaching 0, you provide a small quantity of a tracer and then monitor the output. Theoretically the product in a plug flow reactor must come out after exactly after the time residence time of the feed stream, but very often because of the deviation from ideality of plug flow behavior, it might come out almost in a slightly broad zone. You must have noticed also, some of you must have done chromatographic experiments, that very often broadening of the the output is one of the major problem. Essentially the theoretical chromatographic column, adsorption column, must operate as a plug flow reactor, plug flow behavior, plug flow column, but ultimately because of certain non ideality, there is some kind of a broadening. That means the fraction which you are interested gets distributed over a period of time, instead of coming out as in fact ideally it should come out something like in a very short period of time, just like we have put it here, but it comes out in a broadened fashion. And so now although as I mentioned that any of the kind of input can be given, but for analytical convenience we often resort to either a step input or a pulse input, because analysis is, because these random signals analysis ultimate analytical solutions might be difficult, and the step input or pulse input are the commonly used technique for analyzing or getting the residence time distribution for a given flood. Now the response of a step input of the tracer is usually called as a F curve. That means this F is essentially is equal to C upon C naught. Let us say if your initial concentration is 0 and C upon C naught goes to 1, that means the concentration of the tracer is C naught, and so C upon C naught is 1, and this is given let us say over a period of time. Now ultimately its response you get something like this, and of course with the average mean residence time of T var, this is of course time, and F is essentially C upon C naught. And of course here F is equal to 0 to T E dt, and obviously over a period of time this continues, and or df over dt is the excitase distribution. The differential of the function f c upon c naught is essentially the on the other hand, the response of a delta input is called C curve. In fact, essentially or rather we normalize it to get the response. For example, normalization in this case is C bar is equal to C upon Q. If Q is the total quantity of a stimulus given and then its response is monitored in the time over the period of time, and that is called your, now Q is the total quantity of the input that is given, and therefore 0 to infinity C bar dt is equal to 0 to infinity C upon Q into dt. Now essentially we plot as C bar as equal to C upon Q, the fraction of the tracer which emerges at any given time, fraction of the total tracer which has been put in, which emerges at any time given t, and that is essentially equal to C upon Q dt will be equal to 1, or Q is equal to 0 to infinity C bar dt.
So what is C, Q and C?
See, C is the concentration of the tracer which is in the output stream at any given time t, and Q is the total quantity of tracer that has been put in.
Quantity in what, sir?
For example, here you are not putting continuously, you are putting only in one shot. Say for example, you have put in 1 gram of, let us say, some inert dye into the reactor at any given time in the initially, and after that you monitor its output response. Now this 1 gram will essentially not, theoretically if it is an ideal plug flow, it should come out in a small short period of time, in as much time it has been fed in, but it will not emerge in one go, it will come out in small lots. And if you analyze the output stream over a period of time, and let us say you get such a profile, and where this profile is in terms of the C, which is the output concentration at any given time t, divided by the total quantity which has been fed in the normalized way, and that is essentially C bar, and C by Q the normalized concentration of the tracer output in the feed in the effluent stream, exit stream, and that gives you the C by Q versus T gives you a C curve, which essentially shows the performance of a plug flow reactor in the as a response to a pulse input.
So in the F curve, the C naught represents the maximum amount.
In the case of F curve, the C naught is the maximum concentration which has been, and that concentration is reached instantaneously. Up to some time when there is no concentration of tracer, suddenly at a given time we start a stream containing the tracer, and so it becomes, here it becomes C naught. So C by C naught is 1, and from then onwards the input is same and the output stream, theoretically it should also come out like this after a time t, it should also come out in a constant stream, but it does not come out constant stream, there is a kind of a transient phase till it reaches to the constant stream, and that is what it defines. Now this tracer information can be used directly or in conjunction with the flow models to predict the performance of the real flow reactors. Now theoretically the ideal reactor performances we have been looking at in terms of the reaction kinetics, that means we develop a sort of a mass balance equation for a particular reactor, apply the reaction kinetics and sort of analyze the equation and get the final reactor performance equation in terms of tau versus the fractional conversion or the remaining substrate concentration in the reactor. Now these excitase distribution also can be used to determine the reactor performance based on the flow profile along with the reaction kinetics. Reactor performance from RTD also can be obtained, and of course one can compare, if you consider the ideal reactor flow profile and also the real reactor flow profile and compare their performance, and comparison will give you the deviation from the ideality. Now if you look at, let us say the C curve, which is very commonly used for analysis of a packed bed reactor. Now in the case of a C curve, on the basis of the flow pattern, the mean concentration of the substrate in the exit stream will be equal to the sum of all these elements of the exit stream for concentration of substrate remaining in an element of A's T plus dt into the fraction of exit stream which is of A's T plus dt. Now, that means, now if you just take a differential element of the fluid stream which passes through time dt. So, whatever the concentration of substrate in that stream which is passing through time dt multiplied by the fraction of the exit stream which is of A's between t and dt and t plus dt, and that will give, and you sum it over the all the elements. Now, essentially this is the concentration of the substrate in one element of the A's which is of t plus, which is of A's dt between t and t plus dt, and the fraction of the exit stream which is of the A's between t plus dt, that means of dt during the time dt, and if you multiply the two you get the mean concentration of substrate in the exit stream, and if you sum it up these ones over all the elements or integrate it, you get, or essentially your S bar will be equal to t is equal to 0 to infinity S element into E dt. Now, basically this is the fraction of stream E dt, this is the concentration of substrate remaining in the element, this is S element is the concentration of substrate remaining in the element which is of A's t plus delta t, and this is the fraction E dt which is of A's. Now, these two terms indicate the concentration term as well as the A's term in the reactor, and essentially the mean concentration, the mean substrate concentration in the reactor will be given by this. Now, obviously if you write for a first order kinetics, your S element will be equal to S0 e to the power minus kT. Now, if we can assume, let us say this k is your V dash m upon k dash m, a first order rate constant for the enzyme reaction, and you can also write, therefore, here your S bar from the kinetic for this from the RTD data will be equal to S naught e to the power minus kT into E dt. Now, that means essentially what it amounts to, that if you have a, let us say, a residence time distribution, that means if you have a residence time distribution for any real reactor in the form of E dt, and if you also have, let us say, the rate constant k, the first order rate constant which can be evaluated for an enzyme reactor for enzyme reaction, and you can get this sum over this over all the sort of fractions of the reaction, fraction of the stream, exit stream which has been collected, and you sum it over it, you will get the mean age distribution, the mean substrate concentration in the exit stream. Now, if you notice that normally a residence time distribution, a C curve will be of this type, that is your, if you collect, let us say, normally in the practice what we do, we let us say operate a reactor, assume that we are making a feed from the bottom, and at, let us say, some concentration S naught, this is S. Now, suddenly at any given time t, a tracer is inserted into the reactor in the feed stream over a short period of time, and the concentration is monitored in the exit stream. Now, at time t is equal to 0, 5, at equidistant time, if you determine the concentration of the tracer, whatever values comes at equidistant time, and if they are plotted in terms of again C upon Q, that means you consider the C delta t, sigma C delta t as equal to Q, the Q will be equal to sigma C delta t. Now, essentially here is also a check that this sigma C delta T of all the data must be equal to the actual quantity of tracer which has been put in. If there is any absorption of some tracer into the system or some reaction taking place, or if the tracer is not a good choice, that means either it is participating in the reaction, in that case the total amount of tracer which has been put into the reactor will not be equal to sigma T delta T, and obviously such an analysis is erroneous in nature, which should not be accepted for determining the flow behavior. And essentially one should check that the total quantity of tracer which has been put in matches with the tracer quantity which has come out in the output stream, and which is sigma C delta T, and one can do that, and essentially then one can substitute or write down this integration term in terms of sigma S0 into e to the power minus k into t at different time of t, and sum it over, and you will get the concentration of the substrate remaining unreacted in the exit stream as a function of flow behavior and reaction kinetics. Now on the other side, now the same performance can also be judged by your purely kinetic analysis. That means as you notice that in the case of a plug flow reactor, tau is equal to S naught 0 to x dx over k into S, let us say, I mean the classical balance equation which gives you the performance of a plug flow reactor, and from this one can write S is equal to S naught e to the power minus kt. That means because in the case of a first order reaction there will be an exponential consumption of substrate with time, and therefore now essentially if one takes a real data of a particular plug flow reactor based on kinetic analysis and based on experimental value. Now these will be actually based on this will be actually based on experimental data. Sometime one finds that there is a large deviation, that means this performance will be inferior than this one if the reactor is not an ideal plug flow. If it is an ideal plug flow, the closeness of these values S as well as S bar will indicate the ideality of the reactor flow pattern, but in case there is a deviation one will find quite a different values, and obviously in the actual reactor performance will be judged by the reactor performance based on the exit edge distribution and kinetics combined taken together. Now alternatively one can also look at, if you consider let us say the characteristic F curves for different kinds of flow profiles. Say for example in the case of A curve you have a typical F curve for a plug flow reactor. That means just like as soon as the substrate concentration or the tracer concentration in that plug flow reactor has been inserted after time t or qt over v, or that means one residence time, the substrate the tracer must come out in the same concentration in the case of a step input. In the case of a plug flow with some axial mixing, that means a non ideal plug flow, the behavior instead of being like this it may be something like this. That means the sort of the output becomes instead of vertically averts a curved one, and the deviation of this from the vertical absorption gives the non ideality. In the case C, this is the performance with a perfect mixing, a exponential output of the tracer from the reactor after putting in after time 0. As soon as you put in, there will be a dilution or mixing taking place, and the tracer will get diluted, and from 0 concentration it will come to a concentration, finally all the tracer will come out. On the other hand, if there is a mixing with some dead zones, some stagnant zones, again the mixing pattern might get unchanged. So these are the two non ideal flow patterns, and these are the two for plug flow as well as for well mixed conditions, the exit edge distribution in terms of F curve. Now if you want to quantify the deviation from ideal state in terms of F curve, earlier we have seen the use of a C curve for getting the reactor performance for now. If you want to identify detect the deviation from the ideality using the F curve, then if you consider, let us say a CSTR, a continuous stirred tank reactor, and given a step change in the concentration of a tracer in the feed stream, the exit concentration can be described by, or let us say we consider a stirred reactor of constant volume of a volume B, where the substrate is put, the feed is the product stream is coming out, and then the step input is added, let us say here at a concentration, let us say C naught, and the flow velocity is q. So, therefore, the total mass balance, that is your q C naught, will be equal to q C, that means the C will also start coming out here and at a flow rate of q, plus V dC over dt. That means, the reactor volume there will be change of there will be some accumulation, the rate of change of concentration of C in the reactor, which will go, and therefore, this can be integrated to give you the C upon C naught is equal to 1 minus exponential minus q T upon V, which essentially gives the theoretical output for a step change in a CSTR. Now, therefore, if you make a plot of this curve, a semi logarithmic plot, that means ln C upon C naught or ln 1 minus C upon C naught, you will end up with a slope of your q upon V versus time. You will get a slope of q upon V and an intercept of ln 1, that is your 0. And you can notice that for an ideal reactor, such kind of a reactor, such kind of a response is obtainable. Now, if you assume that there is some kind of a let us say deviation from ideality, and obviously in the case of CSTR the kind of deviations could be of two types. One is that there is some kind of a non mixing, or the part of the stream which is being fed here, let us say Q, a fraction of the stream essentially is going unmixed, let us say this is your F1 or 1 minus F1, F1 is going here, F1 is going into the reactor for mixing, which is getting mixed, and this is volume V, let us say, and now the fraction F1 of the total stream Q is going into the reactor. Let us say the 1 minus F1 fraction is, let us say, getting channeled or bypassed from the mixing pattern, and therefore, one is losing, and another sort of source of non-ideality could be that the reactor may have, let us say, some kind of dead zone because of the improper mixing, and let us say this dead zone is V into F2 or V into F2. Let us say a fraction F2 of the total volume of the reactor is represented as a dead zone where mixing is not taking place. Now, if you write a mass balance for such a system, then you will get your F1 Q into C naught, and of course, again we are, as I mentioned, we are putting C naught as a step input of tracer. Now, F1 C into Q naught will be equal to F1 Q into C, which will come out, plus the fraction F2 into V, fraction F2 into V is the one which is dead zone, into dC over dt. In the case of a non-ideal system which incorporates a fraction of the feed stream into the, which is directly channeled out into the exit stream, and another fraction of the total volume of the reactor which is almost like a dead zone and does not participate in the reaction process.
That will be 1 minus F2 into VDV.
No, this F2 is a fraction of the total volume which is stagnant. See, here the F2 is not of the total feed stream.
F2 is
Of the total feed stream, F1 has come into the reactor and 1 minus F1 has gone untouched from the reactor. Now, of this, the total volume of the reactor V, a fraction F2 is a dead zone.
So earlier there was no dead zone. So we had the whole volume
Yeah,
V.
we had the whole, now because we have a dead zone.
Non-dead volume will have there, sir. 1 minus F2.
Oh, okay, then we can write probably, okay, let us see this is 1 minus F2, the total the active volume, and this becomes 1 minus, sorry, this becomes F2 into V. So, if the total fraction, let us say F2 is mixed, well mixed, and so 1 minus F2, yes, 1 minus F2 into V is the dead zone. So, the rate of change of concentration will be your F2 into V into dc over dt. Is that right? F2, that means you have to define.
So F2 is the fraction that is a dead zone.
That is, no, F2 is the fraction which is in the mixed zone. Ulta हो गया actually. The F2 is the fraction which is in the mixed zone as per this mass balance, of course, which is in the mixed zone. So 1 minus F2 is in the dead zone, and therefore now if you integrate this equation, you will get C upon C naught is equal to exponential minus F1 Qt upon F2 into V, and this can be combined with the outflow stream equation, that means the mass balance equation, as your the F curve, that is F naught is equal to C upon C naught equal to 1 minus F1 plus exponential this minus term F1 Qt upon F2 into V. Now, if you plot this profile, if this expression out the accident distribution C upon C naught, you will get a different kind of a parameter, different kind of profile with from which the parameters F1 and F2 can be calculated. The slope will be minus F1 upon F2 if you plot Qt upon V versus C upon C naught, and the slope will be minus F1 upon F2, and the intercept will be the ln C upon C naught. And yes,
in taking this mass balancer, should we not have the input as QC naught and the output as F1 QC plus 1 minus F1 QC naught?
the input is, because input in the reactor going only F1Q, the other is not going this is not going to the reactor, the 1 minus F1. So, this is the actual input to the reactor, and now this is the exit stream which is going F1Q into C, and plus this is the undergoing change of concentration, and therefore by comparing the two profiles, you can see that what fraction or what deviation, what order of deviation the dead zone and the mixed stream in the reactor has gone into performance. So, that just to illustrate that the use of resistance time distribution in the case of a real reactor can be used to determine the reactor performance, and such a reactor performance then can be used to really calculate or correct the actual performance based on the kinetic data. Now, this is one way to do the account for the non-ideal flow. The other way to handle is to develop the fluid flow models, which of course can vary in degree of complexity depending upon where you can either consider the dispersion as a parameter, and where thereby you can write dispersion mass balance equations based on dispersion and finalize the reactor performance equation. Alternatively, you can also consider as a tank in series model, because a plug flow reactor or plug flow pattern can be considered as an infinite number of CSTRs in series, and a plug flow can be considered as a CSTR in series, and if you can calculate based on the reactor performance the number of CSTRs in series as equivalent to the plug flow, that can quantify the reactor performance. Now, of course, their order of complexity increases from on the basis of the number of parameters considered, but even the resistance time distribution can give you a reasonably good idea of the non-ideality of the flow, and based on which one can even monitor the reactor performance and use that information particularly for scaling it up when you want to go on a larger scale reactors. So, I think we stop at this point.